1.8 calculus is going to seem a little bit daunting. I'm just going to be straight with you. Definitely a little bit challenging at times, kind of daunting. It sounds really kind of crazy, but if you just follow the steps to building up what we need to build up, you can do this. It's not as bad as it looks sometimes, but getting there is a little bit challenging. So just being forward with you right away. We're going to be talking about this thing that's called the squeeze theorem, okay? And a squeeze theorem, or the official mathematical terminology for the squeeze theorem, is here in theorem 1.8, and it's talking about three different functions. One of our functions, called f of x, is completely between h and g. So there's a picture down here where we have h in this tealish color, and we have g in the pink color, and the f of x function is in the black. And we can see that g does its own thing, h does its own thing, f does its own thing right in between, but everybody here at this point has, or even if it's a whole, has the same limit called L. Okay, and that's what the squeeze theorem is talking about. So it says if we have h of x less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing c, except maybe at c itself, so there can be a whole. And if the limit of h is equal to L, as is the limit of g, as we approach c, then we would know that the limit of f is also equal to L as we approach c. And the graph really, I think, helps us see that. We have g, here's our c value, we have g coming here, we have a limit of whatever this y value is from both sides. Same thing with the h function, it's coming up here, and we have this as its L, and as long as f was squeezed, squeeze theorem, squeezed between those two functions, then whatever happens coming right through here, f would have a limit of L as well. Okay, so it makes sense when we kind of see the picture, at least I hope it does. The tricky part is finding those functions g and h that actually will squeeze an unknown function f. So most often we use the squeeze theorem when we're dealing with trig functions like sine and cosine, because we can squeeze them between certain functions. We know certain things about them. It's not very common to use the squeeze theorem for things other than sine and cosine. All right, so let's look at how do we actually apply and use the squeeze theorem. We're going to evaluate this limit here. We have x squared as x approaches 0, x squared times sine of 1 over x as x approaches 0. And this would be totally cool if we could just take the limit as x approaches 0 of x squared. We know that is 0, and we could take the limit as x approaches 0 of sine 1 over x, and we could multiply those if that were possible. But this limit, this second one, doesn't exist. That's undefined. So we couldn't just use those properties that we have been using. There is a real reason for having this squeeze theorem pop up right now. It's, short of using a table, the last resort. So let's see how this works. Because sine 1 over x, this part, is what's causing the problem, we are going to start with squeezing the sine function. So we know something about the sine function, right? You know, no matter what, the sine function does this, and it comes back and does this. So that sine function is always between two certain values, right? So we're going to squeeze that sine function between -1 and 1. So that looks like this. Whoa, that was not what I wanted. -1, less than or equal to the sine of 1 over x, which is less than or equal to 1. So the sine of anything is always going to be between -1 and 1. So whether that's 1 over x or x squared or any numbers of things, that will always be between -1 and 1. Same if that was cosine. So we got that part. We have our sine built in. We're good. We need an x squared. And the rules of equality and inequality work the same way as they did way back in algebra. If I need an x squared next to sine x, I'm going to multiply everything by x squared. So I'm going to negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared. And now the only part that's missing is the limit. So I'm really just starting with what I know about the sine function and building all of these other pieces into my work so I can evaluate the limits on the left-hand side and the right-hand side and then squeeze it to find the limit of the middle part. So I'm going to write this. Limit as x approaches 0 of negative x squared less than or equal to, sorry, that came out kind of messy, less than or equal to the limit as x approaches 0 of our sort of target function and limit as x approaches 0 of x squared. Now it's a lot of writing, and yes, you need to do all of this writing every single time. I don't have a lot of them for you on the worksheet, but it is super important. Remember, notation is key in AP Calc if you want to get the right things. Okay? Now, this left-hand side, the limit of negative x squared as x approaches 0 can be evaluated by direct substitution. So that whole limit just turns to 0. The middle one is the one that we can't do, so we're just going to write it one more time. And the limit on the right can be evaluated using direct substitution as well. So we plug in 0 and we get 0 there. Now, if the limit as x approaches 0 of x squared sine 1 over x is greater than or equal to 0 and also less than or equal to 0, then we know, therefore. Has anybody ever told you those 3 dots in that pattern means therefore? Well, it does. So therefore, we say, by the squeeze theorem, the limit as x approaches 0 of x squared sine 1 over x is equal to 0. Okay, this is what we wanted, and all of the rest of that was the work in getting there. Okay, and yes, you have to write therefore by the squeeze theorem because it's kind of sort of a proof in some aspects. You know, that you have to convince everybody that this is actually the way you do things. So therefore by the squeeze theorem, limit stuff you want as x approaches 0 is equal to whatever number you come up with. Okay, let's look at some more because practice is only going to make us better. All right, we have this function on the left, x squared cosine 20 pi x, and the limit as x approaches 0. So again, we probably have some things that aren't really going to work very well there. Maybe we could just try direct substitution, plug in 0 and cosine of 0 and see what we get. But instead we're going to use squeeze theorem. Okay, so we have a cosine again, and cosine is much like sine. It has boundaries of -1 and 1, so we're going to squeeze our function cosine between those two values. So I'm going to leave all of the argument in there, the cosine 20 pi x, and it's between -1 and 1. So those two functions, -1 and 1, are just giving a big old hug to our cosine function, whatever that cosine function looks like. Same idea, we're going to put multiply by x squared. So negative x squared less than or equal to, I forgot the x squared, And then we get the limit in here, and I'm kind of running out of room. Limit x approaches 0, negative x squared less than or equal to limit x approaches 0. And last one, like that. So we know the one on the left is 0. We know our inside stuff isn't going to change, so we're just going to write that one last time. And this is 0. And then, therefore, by the squeeze theorem, we can now say the limit as x approaches 0 of x squared cosine 20 pi x is 0. So a tedious process, yes. Difficult, I hope not. Okay. This next one, same idea. We're starting with a sign. So we're going to squish or sandwich. Sometimes they call this the sandwich theorem. Sine of pi over x between negative 1 and 1. We're going to multiply by that radical. So I would have negative square root x cubed plus x squared less than or equal to x cubed plus x squared sine pi over x and square root of x cubed plus x squared. Then we do the limit of all three, and I will definitely run out of room. My pen seems to be clicking today. All right, and then we get to evaluate some limits. So we plug in 0, 0, plus 0, square root of 0, 0. This one gets to be 0. Now you're probably all wondering if the squeeze theorem always gives us a limit of 0. And based on all of our examples so far, it kind of looks like that. But that is false. The squeeze theorem can give us other limits. I've just chosen, apparently, all examples that give us 0. So by the squeeze theorem, the limit we are looking for, x approaches 0, of x cubed plus x squared sine pi over x, is equal to 0. All right. So again, super fun, a lot of writing, but you can handle it. This one's a little bit different. Okay, we're not trying to find two functions that squeeze or hug or sandwich our function. We are given two functions and told that an unknown function f is between it. And this is for all positive x's. So somewhere along the line this is going to be needed. So all x greater than or equal to 0. And we want to find the limit as x approaches 4 of that mysterious function that we don't know about. Okay? We already know f of x falls between these two. So I need to take the limit of all of them to figure out where that limit is. So limit as x approaches 4, because that's how it was given over there, of 4x minus 9 is going to be less than or equal to the limit as x approaches 4 of f of x, what I'm trying to find, and then I need the limit as x approaches 4 of this quadratic. Okay, now this limit on the left can be evaluated using direct substitution. So 4 times 4 is 16 minus 9 should be 5. Middle limit just gets rewritten again. And then we have our last limit over here, which hopefully is 5, but we should probably check to make sure. So, oh wait, I subtracted wrong. 16 minus 9 is 7. Good thing I caught that. Now 4 squared minus 4 times 4, so 16 minus 16 plus 7, that one's 7. So now, check that out. We didn't get a limit of 0. Now we're saying our limit is greater than or equal to 7 and also less than or equal to 7. So therefore, by our favorite squeeze theorem, the limit of some unknown function, f of x, is 7. Okay? So, 2 things we learned. Do math correctly, and also, not always will your limit be 0. See what we got on this last page? Ooh, a proof. Everybody loves proofs. Okay? One quick last example to prove that the limit as x approaches 0 of x to the 4th cosine 2 over x is equal to 0. So you're going to start this the same way. If you want to test whether you can do it or not, I would pause the video right now. I will continue working, and then you can start it back up to see. So if you want to check out your ability, pause now. Okay, so just because this is cosine, we're going to squeeze it between -1 and 1, as we have been doing for the entire video. Then we're going to multiply by x to the 4th, so I get negative x to the 4th less than or equal to negative x to the 4th cosine 2 over x less than or equal to x to the 4th. Now we got all that in there. Now we can take the limit as x approaches 0 of all of our functions. And we can evaluate the limits on the 2 outsides. So direct substitution, 0 to the 4th is 0. Why do I keep writing negative x to the 4th there? That's silly. It's positive. And that limit is 0 as well. So, our proof. We did all of these algebra things, so this is not like a geometric proof where you're, giving reasons for each step. You're just doing the algebra. We can see what you're doing. We're mathematicians. And at the end, you just give your therefore statement that we have been doing. So therefore, by the squeeze theorem, you can abbreviate theorem that way if you want. By the squeeze theorem, the limit as x approaches 0 of our function is equal to 0. And remember that every proof you ever did in geometry, or even the ones you did in pre-calc, the last line has to state exactly what it is you're trying to prove. And there we finally give our reason by the squeeze theorem. So that's a proof. We don't do those often, but good to know. Let me know if you have any questions. Remember, you can watch your videos for this section on the AP Classroom as well if you need a couple extra examples or a different way of explaining. Let me know if you have questions, and I'll see you later.